As an illustration of verifying Stokes' theorem, which really is a mathematical result and does not require any verification at all, but it helps sometimes to verify things to see how difficult the left-hand side would be, but the right-hand side is really easy. So let me indicate what Stokes' theorem is. Stokes' theorem is the contention that the line integral of a vector field, in this case it's f, so I'll just write it as f dot dr, is going to be equal to the surface integral over the surface of the curl of f dot n d sigma. As you saw in the previous video, this has a lot of physical applications. One of the applications also is work done by a force, and the work done by a force around a closed path is 0 if the force is conservative. A force is called conservative if the curl of f is 0. If the curl of f is 0, then it also turns out that the work done around a closed path is 0, and therefore also you can show from material that we're going to do next week that the work does not depend on the path you take. Any two paths, for example, if you are in a gravitational field, the work done lifting this pen straight up is going to be mgh. You can also take it all the way to China and eventually bring it up to the same height. It'll again be mgh. The path taken does not matter at all. So what we're going to try to do is, one of the consequences of the conservative forces theorem is that the left-hand side of Stokes' law is always a harder thing to do. We are not going to be doing the left-hand side of Stokes' law incidentally in this computation. We're just going to be finding the path integral from 1, 0 to 0, 1. That is not a closed loop. But one of the consequences of the conservative forces theorem is that the closed loop integral is 0, and one of the consequences of that is in turn that f does not depend on the path taken. So I'm going to write that chain of implication here. F conservative implies that work done does not depend on path taken. So the tack we're going to follow in this exercise is we're going to find the work done by the force along path gamma 1, and then we're going to find the work done by the force along path gamma 2. The same example I have also done in my notes for a third path gamma 3, but I just want to stick for purposes of time in this video to those two paths. And then we'll find out, after doing the work done in each of these two paths, the work to be the same. And then we're going to ask, is this a coincidence or is there a deeper meaning behind this? And then when we find out what curl of f is, it'll turn out to be 0, and that's how we'll know, oh, that's the reason why the work does not depend on the path taken. So that's the purpose of this video. The nuts and bolts of it is what's going to engage us for the most part. How is work computed? So we're going to first find the work done along path gamma 1. Let's first describe the path gamma 1. You have the x-coordinate fixed here at 1 and the y-coordinate varying. So it's the union of the line segment 1y with x1, because in this horizontal segment the x value is varying but the y value is fixed, for the rectangular interval x belongs to 0 and 1 and y belongs to 0, 1. That's the description of the path gamma 1. The work done by the force is given by f dot dr without putting that closed loop there. So the work done by the force along the path gamma 1 is going to be the integral along gamma 1 of f dot dr. Well, the dr is dy along this, and it's dx along that. It's important not to write it as minus dx, because in calculus the limits take care of the fact that dx is pointing in this way. The dx itself is a Riemann measure, the Riemann integral measure, and that should not be messed with. That's an important point. So this is gamma 1 f dx, fx dx plus fy dy. In general, you'll also have fz dz, but we don't have 3 dimensions in this example. It's a 2D example. So we have that. Now all we've got to do is integrate this. Fx is that. But remember, if you're going to do this dx integral, y value is fixed. So the integral of, so I'll write this as fx at the value y equals 1 times dx plus the integral fy at the value x equals 1 dy. Now the limits of the integral x goes from 1 to 0. Now that's what fixes the fact that dx is pointing backwards. The limits fix that. dy is pointing up. Well, the limits are going to tell us that. Y goes from 0 to 1. Okay, once we have done that, let's just compute. This is integral 1 to 0 of 2x minus 3, because when y equal to 1 in this function, I'm going to get 2x minus 3 dx plus the integral when x equal to 1 in that integral, x squared just becomes 1 squared. So that's 1 squared dy from 0 to 1. Let's compute these. The integral of 2x minus 3 is x squared minus 3x, evaluated between plus 1 and 0. And the integral of dy between 1 and 0 is just y between 0 and 1. Let's calculate that. 0 gives us no contribution, and plus 1 gives us the contribution 1 minus 3. Meanwhile, this one has contribution 1 minus 0. 1 minus 3 is minus 2, and minus of minus 2 is plus 2, so that total is 3. Let us now calculate the value of the work done along path gamma 2. Gamma 2 is more complicated. It's a quarter arc of a circle. So the equation for gamma 2 can be written as the equation of a circle, x squared plus y squared equals 1, with the understanding that you have the circle entirely in the first quadrant. So I'll restrict my values of x and y to be bigger than 0 always. Integrals of this type, arc integrals, are best done using parametrization of the curve. The proper parametrization of a circle is the cosine and sine functions. In fact, it can be argued that cosine and sine were invented for this very purpose. So let x be equal to cosine theta and y be equal to sine theta, in which case the range of theta is just from theta equals 0 to pi by 2. Once you have that, I get dx. Dx is got by differentiating this. That's negative sine theta d theta, and dy is cosine theta d theta. And the work done by the force along the path gamma 2 is the same thing as before. It's gamma 2 f dot dr. So you're going to get again integral fx dx plus fy dy, except now we have to put everything in terms of theta. So let's do that. 0 to pi by 2. Fx is this function here, 2xy minus 3. So that's 2 times x, which is cosine theta, y, which is sine theta, minus 3, times dx, which is negative sine theta d theta, plus fy is x squared, and x is cosine theta. So that's going to be cosine squared theta, and dy is another cosine theta, d theta. So that's just a bunch of trigonometric integrals. It's not going to be terribly hard, I hope. Let's do this. 0 to pi by 2. When I multiply the negative sign in, I'm going to get negative 2 cos theta sine squared theta, and then the minus of a minus becomes a plus, so I get plus 3 sine theta. And then what I'm going to do here, anticipating some simplification because I don't want to deal with cosine cubed, so I'll write that as 1 minus sine squared. That's a good way of writing cosine squared. In which case I'm going to get plus cosine theta minus sine squared theta cosine theta. We're not completely out of the woods yet because we're getting something like 4 cosine theta here, and that's a good thing. Well, not 4. You're getting 3 sine theta and cosine theta. These are easy to integrate, but you also have that. So a u substitution must be done for that one. So what I'll do is I'll put this as integral 0 to pi by 2 minus 2 cosine theta sine squared theta, and then you have minus 1 of the same thing, so that gives me minus 3 sine squared theta, and I'm going to write cosine theta as d sine theta. Well, that's always true, is it not? And then the remaining 2 integrals I have are just the integral from 0 to pi by 2 3 times sine theta d theta, and the integral from 0 to pi by 2 of cosine theta d theta. These can be easily done. So the u substitution I have is sine theta equals u, and that's going to give me 3u squared du. The integral of 3u squared du is just u cubed, and u is sine theta, so that's just sine cubed theta from 0 to pi by 2. Well, these integrals can be done by sight. The integral of sine theta is just negative cosine theta, so that's negative 3 cosine theta from 0 to pi by 2, and the integral of cosine theta is just sine theta, so that's sine theta from 0 to pi by 2. Let's evaluate all this. Only the top part contributes, so that's negative 1. Here the top part does not contribute, but the bottom part does, so that's going to be plus 3. And here the top part contributes, but not the bottom, so it's going to be plus 1, and the answer is 3. So you might suspect, okay, there's something deep going on. This cannot be a coincidence. You have a completely different path, which is a straight line here and a curved path here, and the work is coming out to be the same. There must be some magic going on. And the magic indeed is there. We have to show now that curl of f is 0. The calculation of a curl occurs by consideration of a determinant. So the curl of a vector field is defined as follows: I hat, j hat, k hat, del x. The partial del x means del by del x, del y, del z, and then the functions you have. Fx is 2xy minus 3, fy is x squared, and fz is 0. Now, although there are many fancy ways of finding determinant, I like to stick with the basic method of finding determinants precisely because you want the I hat, j hat, and k hat component. If you use any other fancy way of finding determinants, for example, there are all these topological methods of wrapping around the major diagonal minus minor diagonals, then the I hat, j hat, and k hats will be all over the place, and then you'll have to gather them around. So I don't want to deal with that mess, which is why I like to stick always with the traditional method here. I hat times del y 0 minus del z x squared. Remember, that's a plus, that's a minus, and that's a plus. Those are the minor assignments of the cofactors, so sign assignments. So j hat del x times 0, operating on 0 rather, del z operating on 2xy minus 3. Plus k hat operating as follows: del x operating on x squared minus del y operating on 2xy minus 3. It's pretty evident that this is 0, because that's 0, since partial with respect to z of x squared is 0. That's 0 and that's 0 because there's no z in this function. This is the only term where things might seem to be trouble. So let's calculate what this is. This is k hat times del x x squared, that's 2x, and del y 2xy minus 3, that's also 2x. So that's also 0. This shows us that f is conservative, and if f is conservative, then the line integral of the f dot dr along a closed curve is 0, and as a consequence of that, the work done does not depend on the path taken. Any path, even if you have chosen a very crazy path like this, will give you the same work. But of course, you don't want to get stuck doing the work done by this crazy path. It'll take you all your life.